Hello guys, welcome back to my channel Gamma Digamma. I hope you enjoyed the last video about eigenvalues and using them in a differential equation of mechanics and basically characterizing the system by bunch of equations. So let's get started with today's video. Okay, so let me give you a brief background of what inspired today's video. So in case you've been avid and have checked out my complex analysis playlist, you might find this video here, contour integration basic. Yes, that video. So since I study at Cornell and I needed some feedback for my videos, because these are topics, especially complex analysis is a topic I haven't had much formal training in. So I approached a nice professor at Cornell named Strogatz, who was teaching a engineering level multivariable calc course. So I approached him because I know he's really cool. He actually is, and he has his own website, he has his own YouTube channel. He's been invited to a TEDx event where he talked about applied mathematics and learning from nature, and it was really interesting. So yes, this guy. So I approached him, and he works in the Department of Applied Mathematics at Cornell, which is where I was studying. I approached him, and he saw this video because I had put link of this video in the email I sent him. So he saw this video and he had some things to say about it. Feedback, constructive feedback is always valued. I tell this to the people commenting in the comment section because I've seen people bring out some errors that I didn't notice until after I uploaded that video back then. So any constructive feedback is highly valued from anyone, and feedback from a full-fledged math professor is the stuff of dreams. So anyways, so he had some things to say about the way I handle my estimation lemmas. Basically, when I'm trying to show that the function integrated on the semicircular arc goes to 0. Well, apparently I made some errors, some conceptual errors in that case. So that's why this video is sort of like a rectification video for all the wrongs I've done in the past, when situations like this arose. And this man has been really helpful. He's been one of the few professors to actually reach out, take the initiative, actually explain this to me on a Zoom call during this pandemic. And since he already featured on 3 Blue 1 Brown's channel, and he talked about the brachistochrone problem, which was something you all should look into and which was useful for me when I was trying to write an essay on something else. So yeah, that you should actually check out that video. And he'd even invited 3 Blue 1 Brown to be a guest in one of his lectures, and since I wasn't in his class, I snuck in and tried to promote my channel because 3 Blue 1 Brown, I got the inspiration to create my own channel looking at guys like 3 Blue 1 Brown, Dr. Payam, Flammable Maths, Black Pen, Red Pen. So these guys are like my heroes. So I tried to promote my channel to 3 Blue 1 Brown, but Unfortunately, he was too, busy to check it out, which is understandable. But anyways, I tried. That's what's important. Okay. So let's get started, with the feedback he gave me and the rectification I have in place. So this might be a great relief for those guys who had this in their minds, people who were trained in complex analysis and then they actually saw that error evident again and again, but they didn't point it out or kept it in them. That's why I tell you, if there's any error I make, please point it out. I'll pin your comment or give you credit for it. Let's get started. Okay, so the general theme is as follows. We are integrating a function f of z dz on some semicircular arc, because that's what happens when we're doing some contour integrations. We usually, I'm saying usually, not always, have this say this region of integration. We go from minus r to r and then this semicircular arc gamma, and that's why I'm saying it's usually a semicircular one for most of the ones we've done. But anyways, so this is the general setup, and f of z can be expressed as a smaller function g of z multiplied with some exponential part. So e to the I az, that's the general layout of the function, which has some smaller function g of z and some exponential part to it. So now what I'm gonna do is just gonna write it inside the integral. So integral over gamma g of z e to the I az dz. Now let's try parameterizing it. Let's take z equals r times e to the I theta, and theta will go from 0 to pi because it's a semicircular region. Integral over gamma, let's make that integral from 0 to pi, g of r times e to the I theta e to the IA r times e to the I theta dz is just going to be ri e to the I theta d theta. So ri e to the I theta d theta. Now we were interested in, actually, and we always are, the absolute value of this integral over gamma of f of z dz. And by inequalities, this is going to be less than integral of the absolute value of f of z dz. Well, it was actually f of z dz and the entire thing under one absolute value, but I just use Cauchy-Schwarz. I just skip that Cauchy-Schwarz step and then split the product up. Okay, and then this is precisely integral from 0 to pi, absolute value g of r times e to the I theta, then e to the IA r e to the I theta. Fine, we have absolute value of r I e to the I theta d theta. Absolute value of d theta will just be the same. Okay, well, absolute value of I and e to the I theta will just become 1. We have g times r times e to the I theta. Then I can take an IRA outside. E to the I theta by Euler's identity is cosine theta plus I sine theta. which is still under in the absolute value, take the r outside, d theta. Now I would like to say that this function achieves its maximum, or it's rather the way to say it is it's bounded. So g of r times e to the I theta, the absolute value of that is less than or equal to some max of r on this interval of 0 to pi. Let's say it's bounded, so it's a valid assumption. We don't want it to, like, diverge. So I'll have r and then mr, integral from 0 to pi, absolute value of e. Now split this up, distributive property, e to the I times ra cosine theta multiplied with e to the negative ra sine theta d theta. Now e to the I times some value, the absolute value of that is always going to be 1, because this will just be cosine theta plus I sine theta. You take the absolute value of that, you're going to get 1. So this guy goes away, but I'm afraid we can't do this with this guy, and this is the critical part of today's video, because before I used to just take this, just remove this and say assume that it went to 1 like this guy, but that's actually an incorrect approach to have. I'm removing the absolute value because exponentials are always positive. This guy is real too, so real and positive, you don't need the absolute value anymore. Now I would like to do one thing. I would like to split this interval of 0 to pi as 0 to pi over 2. That's because this sign is sort of changing at this cusp of pi. The way I like to think is you have this interval 0 to pi. Well, sign is increasing from this part and then decreasing. So let's just keep one phase of the sign, like the increasing part of it. And interesting enough, integral from 0 to pi of a function like this is just 2 times integral from 0 to pi over 2. That's because of symmetry. Like you're increasing from 0 to 1, and then you're decreasing from 1 to 0, but the net area covered is the same in both cases. It's just the increasing and decreasing happening. Is like, so the minimum value occurs first, and then here the minimum value occurs last. So because of that, I can see symmetry. The integral from 0 to pi just becomes 2 times integral from 0 to pi over 2 of e to the negative ra sine theta. And you might say, just why pi over 2? You could have just kept it pi and whatever, just done something with it. Now here's why. This is the main part. This is what's called the master stroke. It's called Jordan's inequality. It's not Jordan. It's not an American name. It's Jordan. It was a French mathematician. Hence the pronunciation is weird. So now Jordan's inequality says that sine of theta is greater than equal to 2 theta over pi. The way I like to think about this is, take the Taylor series of the sine, absolute value of the sine. It's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. Well, sine of x, which equals this series, is always going to be greater than or equal to x, absolute value of x, because this series has these additional positive terms of x to the 5th, x to the 9th and stuff like that. That's why it's always going to be greater. than a simple x. That's why we have this. But now the issue with just having an x is that on the interval 0 to pi over 2, remember the small angle approximation that engineers make? This is pretty dominant, I would say, or pretty prominent, because this we're pretty close to 0 to start with. That's why we're gonna just glance. Initially we're just gonna like glance on the sine function. We're not gonna be under it, and we want something to be under it because we want it to be less than. We're gonna glance the sine for most of the interval, and I want to demonstrate this fact graphically. That's why we just don't take an x, we take x and a factor that's less than 1. 2 over pi is less than 1. So then that's how we make the slope lower, and then we are under the sine, not glancing it or not just touching it. As I said, I want to show this fact graphically. Okay, so you see here we have a sine of x, the regular sinusoidal function, and y is equal to x, as I said. So as I said, it's just glancing over here. It's just glancing. But if we have y equals 2x over pi, for example, then you see it is going under. Sin x is gonna be greater than this third function that I've graphed, at least on this interval of 0 to pi over 2. If you want, I can demarcate the pi over 2. And you can say that this was some sort of like midpoint theorem or mean value theorem for at least this part of 0 to pi over 2. Sort of like the average value or something. But that's the master stroke in today's discussion. And that's precisely why I'm going to use this inequality, and you'll see how this works out. So going back, forget the trash in between. Going back, 2m sub r and nr, integral from 0 to pi over 2. Now instead of, so wait, we know that sine theta is greater than or equal to 2 theta over pi. A negatives will just flip the sign, inequality, and then you can just have this in the power of e, and the inequality still holds. So e to the negative 2a r theta over pi d theta, and if you evaluate this, it's going to be less than or equal to pi over a times m sub r, and that was essentially absolute value of integral over gamma of f of z dz. And then the checkmating step for this problem was to take the limit as r went to infinity, and then that made this entire thing go to 0. That's basically, I wouldn't say the statement of Jordan's lemma, more like the explanation behind it. Because if you want the statement, I can write the statement. It goes like, if you have a complex function f of z on some semicircular contour CR, which is defined as r e to the I theta, such that theta belongs to the interval 0 pi, both inclusive, and f of z can be expressed as g of z e to the I a z with some exponential basically and a smaller function. Then Jordan's lemma guarantees that absolute value of integral of over c of r f of z dz is less than or equal to pi over a times m sub r, where m sub r is the maximum of absolute value of g of r of e to the I theta. Well, this is so assuming g of z satisfied this condition over here, we can directly, without any hesitation, just reduce our expression, this expression, without showing all these steps, into this guy. That's what the Jordan's lemma guarantees. We just need to satisfy this one condition. Now, another thing to note before going on is, if a is equal to 0, a was this guy over here, so if a is 0, the exponential part will become 1, so f of z will just become g of z when a is 0, and that's when we need to use the estimation lemma. So the estimation lemma, or rather a raw version of it, was what we were using all this time in all my videos to show that the integral over the semicircular arc went to 0. And in the estimation lemma, it essentially says that if you can find the max of this guy, if you can find the max of this guy, then the entire integral goes to 0. So the estimation lemma again says that if you satisfy this condition, then directly you can say that this integral goes to 0 in the limit. In the limit that r goes to infinity. So there wasn't any need to show all the steps like I did in all the videos before. You could have just said estimation lemma, or in this case, in this more general case of Jordan's lemma, that you just end up with this, which goes to 0 as r goes to infinity. So that was the entire discussion about these lemmas and showing that the function went to 0 on this semicircular arc. And special thanks to Dr. Steven Strogatz for really explaining this to me well. I understood more complex analysis in his explanation than I could have in any textbook, I think. Now I could have ended this video, but I want to do this one particular example in case the fancy abstract variable language wasn't clear to you, and that happens to me too, happens to the best of us. Okay, so say we have the function f of z is equal to z times e to the I pz over 1 plus z squared. So this means that our smaller function g of z is z over 1 plus z squared, and in the language that we used in the explanation of Jordan's lemma, a is p. And if you recall, this is the exact function that I actually solved the problem with in the basic contour integration video on which I got the feedback. So that's why I'm using this as my particular example, because I want to rectify that conceptual mistake I made. Okay, so let's start with, again, we have a semicircular arc as before, gamma. Integral over gamma f of z dz under absolute value is less than or equal to integral over gamma. I'm going to skip a little steps, so just be careful with that. Z times e to the IPZ over 1 plus z squared absolute value dz. Now parameterize this guy. Integral from 0 to pi r e to the I theta e to the I p r e to the I theta over 1 plus r squared e to the 2I theta r I e to the I theta d theta. And we can simplify this, so r squares come out. Integral from 0 to pi, this guy will go to 1, absolute value. Now the cosine will go away because this will just be e to the I PR cosine theta e to the negative PR sine theta. So the cosine will go away because it has I times some weird value. The sine will remain, and in the denominator we can use the triangle inequality in reverse, r squared minus 1. Actually it's mod of r squared minus 1, but I'm just, r is positive so it's fine. And on top we just have e to the negative rp sine theta. This guy will go to 1. Everything apart from the r, basically took the r outside. D theta. Now what's interesting to note is that take r and r over r squared minus 1 and just have integral from 0 to pi e to the negative rp sine theta d theta. Notice that this guy is m sub r, the maximum upper bound of g of z, and you'll know it's true if you basically back substitute over here and then take the inequalities. You end up with this guy. So fine, we're essentially going on the right track, that at least the Jordan's lemma predicted. Okay, so r squared over r squared minus 1. Now I'll have to use symmetry, so we have 2, and then the interval is split, becomes 0 to pi over 2 e to the negative rp sine theta d theta. And now using Jordan's inequality, we have 2r squared over r squared minus 1 integral from 0 to pi over 2 e to the negative 2rp theta over pi d theta. If you actually solve this, you end up with pi r over p r squared minus 1 minus e to the negative 2 rp, and this quantity is always going to be less than 1 entirely, which means that this entire thing is less than pi over p times r over r squared minus 1, which is precisely pi over a times m sub r. And this is exactly the result that Jordan's lemma promised us, this inequality. And then the final place, to just destroy our enemy, take the limit as r goes to infinity. So we have pi over p and then r over r squared minus 1, and this I leave unto you viewers to solve, which is pretty easy if you ask me. This becomes 0. This is actually the right way of doing that inequality, of doing that series of inequalities and then proving that integral over gamma goes to 0. This is actually the right way. So this guy goes to 0, which means the inner guy goes to 0. So integral of f of z dz over gamma is 0. This is the right way. So I hope you enjoyed this video, guys. Please write down in the comment section what you think about Jordan's lemma, estimation lemma, or whatever we were doing until now. So yeah, peace out. As always, I urge you to like and subscribe to my channel, recommend me to your friends, spread the word of Gamma Digamma in your math community, and in the meantime, stay home, stay safe, keep doing math, and peace out, people.